question 2.2, limits involving infinity. So we are going to look at, in this section, limits as x goes to positive or negative infinity, as well as limits as x goes to some number and the actual limit, the y value, goes to positive or negative infinity. Okay? We'll use Sandwich theorem real quick in a nice little convenient problem. And we'll talk about end behavior models, which I haven't actually seen it presented this way in the other books I've taught out of, but it's kind of interesting, so we'll take a look at it. All right, so if we're talking about limits involving infinity, why are we beginning with horizontal asymptotes? You've done horizontal asymptotes in pre-calculus. How is that related to a limit?
Because it's a line that the function never actually touches, so it acts as a limit to the function.
Basically, yeah. When we are looking for the horizontal asymptote, we are looking at a function to see what's happening way out when x is huge, either in the positive or the negative direction. So we are taking a limit as x goes to positive or negative infinity. And we just didn't really always call it that in pre-calc. But if we think about this function, which is what function? Is 1 over x. We think about this, and I want to see if there's a horizontal asymptote. Is there one? What is it? Y equals 0. Y equals 0. It is y equals 0. It is the x-axis, what this function is approaching but never touches in this case. And to figure that out, what we're really doing is the limit as x goes to positive infinity, and the limit as x goes to negative infinity. Okay? And if you recall, there were three main situations that you dealt with when you were finding these horizontal asymptotes, but let's throw one more in. What if I asked you about the horizontal asymptote of this function? Is there a horizontal asymptote for that function?
No.
Justin, what do you think?
I think so.
You think no, because?
There's no
True. That may not be the, well, go a little further as to why that would make it so there would be no horizontal asymptote.
Well, like usually like in rational functions, like there's like in 1 over x, but yet that never touches like the x-axis
Because of the x in the denominator. Okay. And tell me about a fifth degree polynomial. What does that look like? Somebody help them? Tell me about the tail. Yeah. Well, it'll rise to the right if it's a positive x to the fifth, but the deal is that one tail's going this way, one's going this way. They are not leveling out to some horizontal value. So with polynomials, we just have to think about the behavior of the type of function it is. Even functions, they're both going to go up or they're both going to go down. They're not going to level out to a horizontal asymptote. So that's why, as Justin said, most often we look at rational expressions when we're finding these horizontal asymptotes. So now let's say we were doing x to the fifth plus 3x plus 7 over x to the third plus 2x plus 1. And if I am looking for a horizontal asymptote, then what I am doing is the limit as x goes to infinity. And we also have to consider the limit as x goes to negative infinity. All right, so I'm guessing you talked about these three situations when you guys did pre-calc. When the higher power is on the top, what happens? When the higher power is on the bottom, what happens? And when it's the same power on top and bottom, what happens? So let's take it one little step further and discuss if we're dealing with x going to infinity, then x is becoming a huge number. And if x is a huge number, then x to the fifth is going to grow much, much faster than 3x and 7, right? A gigantic number to the fifth is far larger than these two. These other terms become negligible when we are at such gigantic numbers. Okay? Same thing's going to happen on the bottom. So the 2x plus 1 become unimportant because the x cubed is so large. All right? So really, what we're looking at to model the behavior, to model what's called the end behavior, is x to the fifth over x to the third. Well, what is x to the fifth over x to the third? X squared. Does x squared have a horizontal asymptote? No. And what is the limit as x goes to infinity of x squared? Does not exist, but goes towards infinity. All right, so if the higher power is on the top, then there will be no horizontal asymptote, and the limit will be infinite. So the limit does not exist. This will approach infinity, so it does not exist, and there is no horizontal asymptote. Well, conversely, let's say we are going to a large negative number. The limit as x goes to negative infinity. Does anything change? No, because again, we have x to the fifth over x to the third, which is essentially x to the second. And if we put in a large negative number, that's still going to go to positive infinity. So this one will also go to infinity, no horizontal asymptote. Okay? All right, well, what's going to happen if I look at the limit as x goes to infinity of x to the third plus 2x plus 1 over x to the fifth plus 3x plus 7. Same idea. Those other terms in the polynomials become unimportant. And we're really just looking at x to the third over x to the fifth as our model for our end behavior. So x squared could model our end behavior. Sorry, not x squared, but 1 over x squared. All right, and what's going to happen to 1 over x squared as x gets cubed? What will that approach? 0. It's like 1 over a million, which is really, really, really tiny, and it goes to 0. So when the higher power is on the bottom, we're going to go to 0.
So does it not get translated anywhere because of the other numbers? Or?
Well, the function doesn't change. The function is still determined by those two polynomials.
Okay.
The whole thing. But what the y value is approaching out at the gigantic x value is really only going to be determined by these two.
Oh.
Okay? So the graph of the function is not what we're messing with. We're just thinking about what's happening way out there. All right, what about if we went to negative infinity? I hear it. What's it going to approach? Still 0. It's 1 over x squared. If we put in a gigantic negative number, we've got 1 over a positive gigantic number. That will approach 0. All right. What if we have the same power on top and bottom? So we have the limit as x approaches infinity of 2x to the 8th plus 3x minus 2 over 5x to the 8th plus 3. Good. And why is it at 2/5, Michael? Yeah, and the basic idea is that the x to the 8th are growing at the same rate, right? If we put in a gigantic number for x to the 8th here and x to the 8th here, the only thing distinguishing what's going on is the coefficients of the leading term. So to find it when we have the same power on top and bottom, we take the ratio of the coefficients of the highest degree. So the limit will equal 2/5. All right, what about if we go to negative infinity? What's going to happen then? Same thing, still 2/5. Questions on those three? Those should be a review. The only thing we're changing now is we're admitting or stating that it is a limit when we were trying to find these horizontal asymptotes. So this would be a horizontal asymptote at y equals 2/5, and this would be a horizontal asymptote at y equals 0. All right, let's see what else we have. Okay, so this one is kind of interesting. What time am I out of this class? Okay, all right. We want to actually find the limit as x approaches infinity of sine x over x. So we found a special limit yesterday, but that was as x approached 0. This one is different. We are finding the limit as x approaches infinity of sine x over x. Well, what happens? Over x. What happens as x goes to infinity? What happens to sine x? Got it? What happens to sine x as x goes to infinity? Well, it's going to oscillate between 1 and -1, right? So we cannot evaluate this by just thinking, let's put in a large value and see what's happening. We can do a little more analysis, but I want to look at it in this one particular way. To figure out this limit, let's remember that sine x, you just told me, bounces between what? -1 and 1. But we are interested in sine x over x, so that would have to be between what and what? 1 over x and -1 over x. So what does it look like I'm set up for here? Squeeze theorem. So let's take a limit as x goes to infinity of each part of our squeeze theorem here. Is less than or equal to, should be less than or equal to. The limit as x approaches infinity of sine x over x should be less than or equal to the limit as x approaches infinity of 1 over x. Stop. Erase right there. All right, well, what is the limit as x approaches infinity of -1 over x? It is 0. Think about putting in a gigantic number here. What's happening? We get 1 over a gigantic number, which is very close to 0. The other way you could think about it, think about the graph. -1 over x is the reflection of 1 over x. So that one goes to 0. Is less than or equal to the limit as x goes to infinity of sine x over x? The one we're trying to figure out. Less than or equal to, what is the limit as x goes to infinity of 1 over x? That is 0 also. So, the limit we are trying to solve, limit as x goes to infinity of sine x over x, is what? Is equal to 0. That's another one that you might add to your list of things to know, because it is helpful in different types of problems. Those are stars. There we go, that's better. Okay. Let's take a look at one more example. If I need to find the limit as x goes to infinity of 5x plus sine x over x, if I plug in infinity, or something that, some real number that's very large, what do I get?
5 over 1 plus sine x over x, which is 0.
So you split it up, so you're splitting it up, but I'm saying if we just plug in as it appears now, what we end up getting, we can represent by infinity over infinity, couldn't we? Okay, so you should know that is your second indeterminate form. Remember, indeterminate forms happen when there's a conflict in our rules. Infinity over anything is usually what? Infinity. But something over infinity is very close to what? 0. So we have a conflict in the rules again. So we call that an indeterminate form. When we get an indeterminate form, we have to change the look of the problem, which is what Tim just did. He said, let's make it the limit as x goes to infinity of 5x over x plus the limit as x goes to infinity of sine x over x. This one we just proved on the last example is what? 0. Our x's cancel, and this one is what? 5, because we're going to cancel that happens here. So our limit equals 5. So 2 different times now we've come across an indeterminate form, which means we need to change the appearance. 0 over 0, infinity over infinity. Okay, find an end behavior model. So this is what we were doing before. When we look at this, we want to find an end behavior model that represents how this function will look at way out when x is large. So these become unimportant, and we end up with 2x to the 5th over 3x squared. So what could we use as our end behavior model? 2/3 x to the left. X to the third, thank you. That's all they're talking about when they ask for an end behavior model. So this function that we're looking at will behave like this function when x is gigantic in the x in the positive or negative x. All right, and how about this one? Just 2/5. We have 2x to the third over 5x to the third. So our end behavior model would just be 2/5. So you may come across questions like that in the homework that ask for an end behavior model. All right. Okay. Sorry, I don't have to read that quickly. What if I was interested in a vertical asymptote? So you told me that we could get a vertical asymptote if we had something like the limit as x approaches 0 of 1 over x squared. So horizontal asymptotes are when the limit is as x goes to positive or negative infinity. A vertical asymptote occurs when the y value approaches positive or negative infinity. Okay, just to keep that clear. And that is it. That's all I have for you. So, homework for tonight is page 76. Long weekend. So you need lots of things to do. 1, 3, 9, 12, 16. This is on the assignment sheet, but if you want to write them down now, you can. 21, 23, 29, 31, 33, 35 through 38, 41, 45, 49, 51, 53, somewhere around 20, 59 through 64.